Have you noticed any anomalies that have come out of applying this?
Well, to be honest, I only used it like 1.5 years ago in a personal project, and it worked very well. So I have no downsides as of now. So I suppose that like there are a lot of downsides of using this, and I suppose you are improving one metric, but you are probably decreasing some other metric that you are not measuring, I suppose.
So I think that back to what you were saying before, like the advantage that this has over a properly probabilistic method that can give you an actual probability distribution with, I don't know, with variational inference or something similar. Well, first you have the problem of tractability, so the variational inference problems tend to take longer to train than a neural network, and then you have the accuracy problem, so they tend to perform worse, even if they are giving you a proper probability distribution.
So that sounds to me like you don't know whether you want accuracy or calibration. Mm-hmm. Do you want to represent the distribution, or do you want the best accuracy?
Yeah, so that's what they're claiming, is that you can have both. So you can have calibration and accuracy, which is not necessarily true, but it's what they're claiming. I think that the main disadvantage with this method is that there is no real gauge on how this will generalize. Right? Mm-hmm. So you know that in your test set you're going to be perfectly calibrated.
In your validation set.
On your validation, but how many validation sets do you need to actually check that the thing is properly calibrated? Yes. So scikit-learn does it with cross-validation approach. So scikit-learn has a calibration module, and what they do is they split the train set in equal parts. They train one model in each. So they train a cross-validation model, and they use all the evaluation sets from the cross-validation to train the calibration. So you have different predictions from similar models but that are slightly different, and then they calibrate on that, and that is how they sort of try to guarantee generalization of that calibration element. But again, it is a layer on top to say, okay, we have this problem, let's put some makeup on it.
Let's hide it.
Yes. But that's deep learning for you.
But it works.
Yeah. By the way, these plots you can easily, well, not exactly these ones, but very similar to this one, the sklearn has all the tools you need. Just go sklearn calibration, and you can like input your actual vector and your probabilities, and it will print you this plot. So it's very simple to visualize. And
there is a demo from last week which shows some of these calibration things. And you're more than welcome to contribute to it. It uses a toy data set, so it's not very descriptive. But if you can take those methods, apply them to your data sets, and report back to us, we would be more than happy to discuss about it, what worked for you, what didn't work. And if you want to extend them, there is an incomplete layer for Platt scaling, and then the proper Platt scaling algorithm. So if you want to add to it, just PR to the GitHub repo, and we can discuss it here. Okay? Discussion point? Okay. Thank you, Joao. Thank you.